Hello and welcome back to Calculus 3. Gotta learn the script. Today we are continuing our discussion on it's not a discussion. There's no discussion. This is calculus, it's math. Yes, I just talk and you absorb like a sponge and then you go home and do problems. That's all it is. So we are going to continue our journey into discovery. No, I can't do that. All right, so we're just going to continue 12.6. Very good. So last time we talked about directional derivative. First, we reviewed the concept that if you have partial derivatives, they are either in direction of x-axis for partial derivative in respect to x, or in direction of y-axis as a partial derivative in respect to y. And they can measure the steepness or the change of the shape above them, which is when you cut through the x-axis, let's say, and the trace line will have derivative all along, which measures steepness. Now, with directional derivative, we are able to measure this kind of change anywhere else, because the directional derivative is going to measure the change in any other direction than x and a y. Now, you can still measure direction x and a y. And we had this formula here, which is the dot product between the partial derivatives in respect to x and a y, computed at the point, which would measure the change at that point, and then the unit vector u1 and u2, which will give us the direction that we want to measure the derivative. Now, and I stated this last time, if you are to use vector 1, 0, which is a unit vector, then you will just keep partial derivative in respect to x. And if you use unit vector 0, 1, then you will only keep fy, partial derivative with respect to y. So this is most general formula that you can write for all possible directions, which also includes the first two directions we learned, which is fx and fy. And then we did two examples, I believe, and then we just left because the class was over and you wanted to go. So now we are going to continue this lecture. We are going to take this special vector fx, which is computed at a, b, and fy, partial derivative, also computed at a, b, and we are going to give that vector a name because it is a very important vector. It's a vector that we will use a lot, and that vector is called the gradient. So that's the gradient vector. And this particular one is the gradient. And now we're going to define the 2D gradient vector. So 2D gradient vector looks like this. Here, I'll write it in blood. So the notation is this upside down triangle with a little arrow above to denote that it's a vector. Now, in your textbook, they're just going to put the bold triangle. We know that the bold letters in the book represent vectors. We don't mess with bold while we're writing, so we just put the arrow above and everyone's happy. So the gradient of the function, in this case in two variables, is going to be the vector of partial derivatives. Oops. So this is it. So knowing this definition, I can recast now notation for our directional derivative by stating that the directional derivative in direction of vector u at AB is simply gradient of the function computed at A, B, dotted with the unit vector u, which has a hat because it's a unit vector. So that's just a new notation for the same concept from before, nothing new. Oops, I dropped the f over here. Directional derivative of f in, all right, cool. So computing gradients is very simple. You just find partial derivative of x, partial derivative of y, and you put them together in one vector. So that shouldn't be too much brain cells for you to accomplish. So say it's the function is given as, I don't know, x sine y squared minus 3x y to the 4th plus 8. So find the gradient. Find the gradient for this one. This.
How does gradient origin to be?
Just as a regular.
What is gradient?
I'll explain. Just let's do this.
How is that location read? Is this gradient up?
Well, oh, the upside down triangle is read as del. I forgot to say that. Del, yeah. Del. No, because it's usually broken. This one works all the time. I know. Ha ha ha. And I wait for the third. No coughing. Okay. So we just find partial derivative, put them together, and that's it. Sorry for disappointment. The question is, what is the gradient? What does it do? What kind of purpose does it serve? We know that these derivatives independently show the change. What is the gradient doing? What is the vector? And to answer that question, we have this theorem which shows the path of steepest ascent or the path of steepest descent, and that's calculated through the gradient. So let's write that out. We'll do it in purple. Everyone is happy. So let the function f be differentiable at a, b, and the gradient different than 0. Let f be differentiable at a, b, and del f be different than 0. So if the function is differentiable and the gradient is not 0, 1. F has its maximum rate of increase at AB in the direction of del f computed at AB. And the rate of change is the magnitude of that vector. So in the light of what we're talking about, previous problem, you have these x's and y's, and you have a and b to plug in. So I don't know, pi and 0, whatever. You plug those values, and this vector will turn into, let's say, 3, 7. I just tossed numbers out there. So vector 3, 7 has two components to it. It has a component of magnitude, and the magnitude of the vector is the one that tells you what's the slope of how steep it is, and the direction, obviously, in which direction it goes. So that's what's captured here. Now, what does it mean for an object? If I have an object, let's take this as an object, and we pick a point somewhere on this object. So you pick a point on the object, and I will keep this object slanted. Maybe this one. So we can find, this is the problem when I'm not using the pens that actually leave a mark. There we go. So looking at this object, let's say it stands this way. Somewhere this way, like this, would be the steepest going up. That's what gradient measures. Because this object can be in any possible way. And this point AB could be anywhere in its domain, and when you shoot that point, will, on the surface of the object, it will manifest somewhere as a point. That's where the Z is. So you'll have ABZ, right? So at that point, whatever it is, there it is. So whatever that point is, the gradient measures. So you take a look at all of the possible vectors that you can get out of here. Which one will be the one with the largest slope to climb? This dot should be an ant. You think of an ant there. What would be the largest slope that this ant would have to combat, right? The hardest way to get anywhere. So that's what it measures this way. It has the maximum rate of decrease in the direction of the negative, right? So number 2, f has its maximum rate of decrease at AB in the direction of negative del f computed at AB. So that's the steepest way down. The rate of change is negative absolute value. And then the directional derivative is 0 in any direction orthogonal to. Now, why is that true? The directional derivative is 0 in any direction orthogonal to del f AB. Why is this true? Dot product, exactly. It's a dot product between the del and the unit vector. So perpendicular means the dot product is 0.
What is the dot product?
The formula we had before, when I recasted everything.
Oh, okay.
So when they're orthogonal, the dot product is 0. So it plays off of the previous theorem that you know. All right, let's test a problem here. Steepest ascent and steepest descent. I'll pick something from homework. Here's a beautiful example, 28. You guys like trig, right?
Yes.
Sorry to disappoint, no trig in this problem.
Yeah.
X squared plus 4xy minus y squared at the point P 2, 1. That's your A and B, guys, 2 and 1. So find the direction of the steepest ascent and descent.
So it's find the gradient. Is that okay?
But you can find the magnitude as well, why not?
Oh, good.
Yes, you can. No, I just changed it. Keep adding. Keep adding more.
I had a wireless keyboard near my bed, so I can use my computer, my PC, from my bed. So if my boyfriend's playing video games, I turn it on and I just start playing with the trackpad.
Yeah. But the best thing to do is to download one of those remote if you have the right cell phone.
Not.
Right.
Yeah.
You download the apps, the remote control apps for TVs. So awesome. You go to your friend's house, see which TV they have, changing the code in the cell phone until it works. They sit down. Off.
But you need friends for that. I don't have friends.
That's true. I don't have friends anymore. When I had friends. And then as a girl, now they're only writing files. That's all be involved in.
They just want to shoot others.
You would say I'm a big target, right?
Yup.
But I'm not saying they can't be wrong. Because I'm like, yeah.
Do you remember when I got into the tube in the middle of the field? Were you there for that?
Yes,
I just killed everyone from inside of the tube.
yeah, everyone's wondering what actually was shooting at them from where.
Yeah,
Because they couldn't
there
see
was
you.
like it was like a barrel on its side with like two there, and like the little 6-man was like, I'm not that fat, I can get in there. So I got in, and I was just like sniping these bitches.
You took out like 3, right?
It's about 4.
4? I'm sorry.
I'm good at sniping. I can. The last time we played, I sniped too. I was stuck in a tower, and like every time I put my head up, they'd shoot me. So I just kind of hit the wood until there was a hole, and then I shot them from it.
That's awesome.
And then they were like, "Who's the dude that was in the tower that kept sniping us? They brought like 6 of our guys." And I was like,
It wasn't a
bright
dude,
pink hair.
thank
It's like,
you.
it was me.
Her hair is pink because of the paintball.
No, it's natural. You want to bet?
Yes, yes, I do.
All right, so
These are my baby pictures. I've always had pictures.
I come in store with these little cigarettes naturally thing.
I'm just going to do this because I can. Do we all have the same gradient vector? Yeah? Okay. So now we compute that at the given point, which is 2, 1. So that's 4 plus 4 is 8. And 0, right? I said 6. 4 times 2 is 8, minus 2 times 1 is 2, so 8 minus 2 is 6, clearly. So this would be the direction for the steepest ascent, so the hardest way up. And the slope of that would be, when we find the magnitude, which is 8 squared plus 6 squared, which is what? 10. Nice. Then we do the same thing with the negative. Well, I need to put the negative. Let's do xy first. So we have that. Then we find negative with 2, 1. So that's negative 4 minus 4 is negative 8. And then negative 8 plus 2 is negative 6, clearly. And we still have 10. Yes.
Minus y2 go.
Why? What do you mean y2? This one?
Yeah.
Right here. The derivative in respect to y is 2y. The derivative in respect to x is 0. So there's nothing there. Empty space. Void. Joe.
Does the D set negative tag?
Yes, it is. There's a negative in front and the negative in front.
You have to find the negative.
Cool.
Because it's always negative outside of the magnitude, but in the formula it had the negative symbol.
Yeah, it's on the outside.
Yeah.
So it's negative always. The formula is the square root. That always gives positive values.
Okay.
Does it always work out to be the same?
Do what?
Does it always work out to be the same but opposite? Or?
Yeah, but it has to, right?
Why?
Because of the negative sign. We're just doing the negative sign in front of it.
But technically, they're not half.
All right, let's take a look at pretty pictures now. So here we have the shape, right? And you can see that there's no change. So this is when it's 0, when it's perpendicular. But if you pick something else, right, the point along this line, you will get the different change. Now, I don't know how visual this is. It's a little bit tough to see it. The way I like to think about these things, especially when you have shapes, is I imagine myself as an ant walking on that surface. And what would be the hardest way to get up? What would be the easiest way to get down, which is, again, the steepest, right? It's very easy to go steep down the right. No effort. All right. That's that. What else do we have?
You say find the gradient if you want positive and negative?
No, for gradient it's just a positive. This is only for ascent and descent when we differentiate between them. Gradient is just a positive one. All right, so with the level curves, there is a proof here involved if you're interested, obviously. Well, the honors ones. So we said that the level curves would be when you cut the object using horizontal plane. So what is the level curve in this classroom? The level curve in this classroom would be this line here. This is the level curve. Because the ceiling is the horizontal plane which cuts through the shape which is this building. So whatever, right, if this cylinder was infinitely tall, you cut it with something straight, and this line along is the level curve. It will be a circle, obviously, in this case. In this case over here is the rectangle for the classroom. So if the object stands on the side, if we cut this object with a horizontal plane, we will have ellipse, right, as a level curve. So you understand level curves from previous chapter, and you know how to get them. To get the level curve, so now we're talking level curve and gradients, So just to iterate, you cut some kind of plane. This is a terrible plane for the cut. Nope, that's bad. So I'm cutting with a plane right there. So if I cut with a plane, this line over here is a level curve. So you have Z shape. So this shape here is Z equals f of xy. And what you do is to get level curve, you cut with, say, Z equals 0, Z equals 1, Z equals 2. Technically, Z equals some value. So you cut with that. So that's how we get level curves. And clearly, as soon as I set Z to be any kind of constant, then my equation just becomes x and y equation, which you can see it's a circle, it's ellipse, it's something. So now what is the theorem says? Given a function f, given a function f, differentiable at AB, the line tangent to the level curve of f at AB is orthogonal to the gradient. Del f at AB, provided it's not 0. The gradient. That's why I'm writing it now. That's okay. So if you take a look at the level curve, so I'm going to give you, say this is a level curve. Guys, this is in a bird's eye view. You are watching this from the top. So what you see now is this. Okay? You see the cut. So technically, where are you sitting? You are sitting on the top of the z-axis and looking down. What you have here, let's say, at this point, you have the tangent line, and then you have the gradient. Technically, pick a point. Tangent line, gradient. So they are perpendicular to each other.
They are on the same plane.
Yes. Because technically that's the only thing that exists, right? When you cut through and you have only A and B, or the two variables, they all have to be in the same plane. So
What makes difference from the normal?
Yeah, but that's in space. So think about it when you have, let me find. See, this is your level curve. This is your standard R curve, parametricized. The tangent on this side would shoot off this way, and the normal will shoot off that way. But the gradient is in the flat surface of the domain where you have the level curve that looks like this sitting on this, right? And it can go that way and that way. So technically, you draw that on the with the marker. I draw it here on still. Excellent question. This is why we do class preps.
Can you just show that real quick with
Not.
With the paper towel?
To what? You need paper towel?
Yeah.
What do you need from me?
Can you just show that real quick with the paper towel?
So this is the object.
Yeah.
Now imagine that I take the sword, cut it here, and I get this. So there it is. Right. So I cut it. I throw the other piece away.
Yeah.
The level curve is this line here. And that lives in a plane which is flat.
Yeah.
So 3 feet. So this was z equals 3 cut. So I take this infinite cylinder, which is z equals whatever the equation is, which is x squared, okay? And I cut it at 3. So now this line over here becomes x squared plus y equals 3.
Yeah.
So now I have the level curve. And then at that level curve, I have the tangent vector that is shooting at you, and the gradient shooting at you. So the gradient vector is the one that's going to radiate like this around, points out, and the tangent vector is the one that wraps.
But if the gradient is measuring the steepness, why is it not?
That measures the direction. If this is to be like this, the gradient is I see where your confusion is. Gradient is on the floor.
Yeah.
Gradient is a 2D vector that points on the floor in a direction where on the object it will be steepest ascend or descend. So me drawing the vector here is bad because the gradient is not on the surface of the object. The gradient is on the floor, saying that if you go that way, right? If you go that way, you will be going up at the steepest, right? So think of it as if you could shine that vector from the floor up onto the object. Does that make any sense? Maybe I can, let me try. So this is your vector. This is the gradient vector.
Yeah.
It lives on the domain xy. And now I'm going to position this that way. This object should stay like this because this is the hardest way up. This is the steepest way.
Oh, okay.
So if the vector is this way, then that has to stand this way.
Okay.
So it's kind of like an XY vector that shows you the direction.
It lives in the domain,
Okay.
which lives on the floor. It's 2D, right? It cannot live on a surface. Surface is 3D. The surface of the object. So we understand maps that way. We understand them. So, right, I have this. It's crazy, right? I pick one point at a time. I pick one point at a time, and then the vector, when I find the gradient, will show which way is the hardest way up and which way is the steepest way down at that point, and changes point to point.
Is the lines on the map when you look at like the 3D map and it has like a bunch of circles and the closer the circles are, the steeper it is?
That's the level curves. Those are the level curves. We did that when we did the level curves
Yeah.
section. That's the level curve. That's not gradients.
The gradient
But-
is the direction the curve is going in.
Yeah. Oh, that's a great thing. Let me find that image. Very good. So let me go back to the section. Was it here?
When you're saying 2D gradient vectors, you just meant that the vector itself is 2D.
Yes.
You're not talking about 2D functions.
Nope.
So it can't have gradient, right?
Where was it? That map image we were looking at.
Isn't that in the goal?
Yeah, looks like. Haha. All right, so you remember these images, right?
Yeah.
It's a steady climb, right? It's a steady climb at equal cuts. We have equal divisions. It's a steady climb. When it climbs slowly and then quickly, the termite things, slow climb, far apart, rapid climb, close by. What is the direction of the gradient here? Yeah. Awesome. So you can actually read the gradient off of those. And then I obviously apply to more complex. Now here's how they look in 3D. I'm sorry, 4D. You have a three-dimensional input, and then you have these colors which show temperature. This is not equal everywhere in this room, right? We have the window over there, so that's cooler than this area over here where we have two computers running, let's say, and me talking and generating heat. So we will have now, after this, we are going to define the third-dimensional gradient, right? Which will show, right, when you go one dimension up and you think of the temperature, so I'm going to pick a point here and show in a 3D in what direction the temperature is changing the fastest in terms of growth or going down. So I can find the 3D vector in that case. So when I have a 3D gradient, it will tell me in which sense the fourth dimension is changing in which way. Does that make any sense? So the 2D gradient shows me the steepest way in terms of the z, right? Hard to climb, growing up, it's z. In the case of 3D now, so this is how it looks like. And you have thermal classes. Any mechanical engineers? There you go. So stuff like this, right? Thermal classes. So you will have a 3D, and for you guys it's essential to understand this because you have to know how temperature behaves to create any kind of machine. You have to know temperature flow and well, that's what thermal is. So in this case, I'm not even going to start imagining how this works. We all know that blue is cold and the red is hot. So what are the fastest ways to get to blue into red, right? So from blue to red, that's fast change, fast change, fast change, fast change, and over here there's no change, right? So those are kind of things that you can. So there has to be a vector from that window towards this side where we say that the temperature is changing up, right? So the positive gradient would be going this way because of that's cold over there and it's hot over here, right? So we are looking for that three-dimensional vector to describe the fourth variable, which is temperature. Great. These are all great questions.
Is there like an analogy to make either like a velocity and something moving?
In which sense? Yeah, which again.
Oh, it's like the steepness.
Think about you let something go and it's just going to go down, right? Where is the fastest acceleration? Like the gravity is going to pull, but then again, you have some friction on it. You can do conservation of energy. Oh, what happened? Physics hit hard? Aww. You should have finished all of the math courses first and then go and just enjoy physics. A joke of physics. How about it? Focus on labs. Awesome. Path of steep descent. We did that. We talked about this. Hey, homework. Hold on. Homework. And there's the 3D gradient. Nothing special. Partial derivative of x, partial derivative of y, partial derivative of z. So 3 of them. So gradient. Let's define it. And guys, we need both of these for our Lagrange multipliers. We'll get there. Yeah, don't worry about it. We're racing towards the topic. So 3D.
Are you writing?
I am writing. I'm writing exactly what you see. But I know you want to see my beautiful handwriting, so here. So again, it's a vector of partial derivatives. Vector of partial derivatives. Without me really copying what's in a book, beautiful example. You have an egg, all right? It's not egg, it's a watermelon. Elliptical, ellipsoid, right? Ellipsoid. And find a gradient and at these particular points on the surface, you want to see what is the greatest change. So you can compute all the gradient vectors, which are these red lines, and you can compute their magnitudes, which are the changes that are happening. What kind of change? Change in temperature, change in pressure, change in whatever you need to compute. I'll leave that to physics and your other courses to enjoy later, especially you guys going into thermal classes. Awesome. And this lecture is done. We are going to take a break, and then after that we'll do one more. Any more questions, concerns, anything? No? So yeah, cool.